Vijay, maybe we can start.
Okay.
Yes, so welcome everyone. So today's speaker is Neha Prabhu from Pune University, SPPU Pune, and she will be talking about the Sato-Tate conjecture for elliptic curves. So over to you, Neha.
Okay. Okay. I'd like to thank the organizers of the seminar and especially Devendra for this invitation to speak in the Saturday seminar. So today's talk, I'll of course tell what the conjecture is, but I'd like to focus on early evidence towards this conjecture given by Birch. And so I'm not going to be proving even though this is a theorem, I won't be proving the theorem, but I'll be talking about a related result to the Sato-Tate conjecture. Okay, so now let's set up the notation. We will first talk about equidistribution of sequences because the conjecture is directly related to that. So if you let X be a closed interval in R, so equidistribution is known in various contexts, but I'll just talk about the one that pertains to the Sato-Tate conjecture. With the probability measure mu. And a sequence xn in X is said to be equidistributed with respect to the measure mu if for every interval in X, let's call that I, we have. So the idea of equidistribution is that you look at the proportion of your sequence elements up to stage n divided by n. So this is the proportion of the first n elements which belong to your interval, and let n go to infinity. And equidistribution means that it essentially covers the whole interval. Okay, so this would be integral I mu of x dx. Okay, so it says that the sequence elements are distributed all over the interval, but in a very sort of systematic way. So in some sense, if you let mu to be the Lebesgue measure, this is a stronger statement than asking for a sequence to be dense. Okay, so you want because if you change the order of your elements in your sequence, it'll change this number as well. Okay, so for a quick example, the sequence n theta. So here I mean fractional part. For theta irrational is equidistributed with respect to the Lebesgue measure. And Lebesgue measure, of course, it just means that this right-hand side would be the length of your interval. Okay. And now the sequence of interest in today's lecture comes from elliptic curves. Okay. So for our we are interested in sequence for from elliptic curves. Okay, so over finite fields. Okay, so so we let P to not be 2 and 3. And for AB in FP so there's a mild condition. We don't want P to divide this quantity, which is the discriminant of an elliptic curve, which I will come to. So let EAB denote the elliptic curve in Weierstrass form. So it's given by y squared, so EAB x cubed plus AX plus B. And it doesn't mean we don't have elliptic curves over F2 and F3. It's just that it'll have a different, it can't be brought to like this particular form. But eventually we'll be taking P large, so it's okay if we ignore the first 2 primes. Okay, so now the FP points, the number of FP points on this curve is given by P plus 1 minus some quantity, which is more standard notation is A sub P of E or A sub E of P. I think I've stuck to this for today's talk. And this is the quantity of interest for us today. What do we know about this? Well, we have the Hasse bound.
How you are defining AP?
Sorry?
How you are defining AP?
Yeah. So whatever the number of points on the elliptic curve is, it's given by P plus 1 minus some quantity, and that quantity I'm denoting as AP of E. And what we know about, huh?
You haven't defined it, right? AP.
Yeah. So these are numbers that we will finally be talking about the distribution of these numbers. Okay, so it's P plus 1 sign minus some quantity, and that's why the study of this becomes important, because we I mean, okay, if you know the number of points on an elliptic curve, of course that tells you what AP of E is. But in general, we don't have like a formula or something. Okay, but I'm coming to the properties of that. Okay, so satisfies the Hasse bound, which is that it is bounded in modulus by 2 square root of P. Okay, so these are some real numbers that have this bound. And if we normalize, we see that, so let me denote it as A tilde. This belongs to minus 1, 1 for every prime P, okay, except the bad primes, what these are called bad primes. Okay, so in other words, it's called prime of bad reduction. So now we have a sequence for indexed by primes for all but finitely many primes sitting in a fixed interval minus 1, 1. So naturally, we can ask, how do these numbers sit inside minus 1, 1? Okay? So it is then natural to ask about the distribution of AP of E in -1. Yeah, this is essentially answered by the Sato-Tate law. So the Sato-Tate conjecture for, so okay, here there's a small technical point where we need to make a distinction if the elliptic curve has complex multiplication or not. But
AP is positive, no?
sorry, sir.
Except E is positive.
AP of E, no, it need not be positive. It can be negative as well. Sorry. Yeah, the yeah, AP of E is positive. Yeah, that's right.
It could be 0, I guess. Yes.
Yeah, but it's yeah, it's not negative. Wait, oh yeah, but so AP of E is no, AP of E could be it's an integer. It could be negative because P plus 1 minus EF of P, E of FP can be negative.
And the 2 root P is usually much less than P plus 1.
Yeah, but it could also be -2 root of P. So then it would exceed P plus 1.
So the previous number of points could be more than P plus 1.
Yeah, what is it? So if we have so okay, let's look at another AP of E would be x going from 0 to P minus 1 plus AX plus B over P, where this is the Legendre symbol. So yeah, it can't be more than P plus 2. In fact, this is plus 1 minus this. And is it obvious that this is I think this would be AP of E can take negative values. I'm a little confused right now, but I'm sure it does take negative values because the distribution does have points on both sides of 0. Okay, maybe I'll come back to this later. Okay.
Yeah, okay, good.
Okay, anyway. Okay, so if I lies in the interval -1, 1, and n, we denote n sub I of Ex as the number of primes up to x, such that A sub E of E lies in I. We want to see the proportion of this when you divide this quantity by pi of x, which is a number of primes up to x. So the Sato-Tate conjecture says that the limit as x goes to infinity, ni of Ex by pi of x is this, the value of this integral, square root of 1 minus t squared dt. And this is also, maybe I'll This is a Sato-Tate measure of the interval, or this is more well known as the semicircle measure. So yeah, so this is so it means that the AP of E are equidistributed with respect to this particular measure. Okay, and this is okay. So it will have it will look like this. This is the distribution it'll cover. If you draw a histogram for a fixed elliptic curve, as x tends to infinity, we'll see the shape of the histogram taking this semicircular shape. Okay, so it's also called the semicircle Sato-Tate measure. Or semicircle measure. Okay, so this is no longer a conjecture. It was proved by Flazell, Harris, Shepard, Barron, and Taylor in a series of papers from 2008 to 2011. Okay, and but so this conjecture was made sometime around 1967, independently by Sato and Tate. And in 1968, Birch gave a result which is sort of an evidence towards the conjecture. Okay, so what he did was he did something. So what it's like a vertical Sato-Tate, wherein instead of fixing the curve and varying the primes, he varied the curves, which I will explain in a bit, and fixed a prime. So he got the distribution for a fixed prime and then let p tends to infinity and showed that it matches with the Sato-Tate distribution. Okay, so he instead looked at the moments. So let the rth moment be, so you vary the a comma b, which is there as parameters in your Weierstrass equation. And you raise it to the power r. Okay, so these would be the moments of the sequence. Little a and little b. Okay, now if r is odd, then this is actually 0, because when you vary the curves, you can pair an elliptic curve with its quadratic twist, and for that the APEs are of opposite signs, and so if you have an odd number here, they cancel, so this would become 0. So it already tells us that this distribution is symmetric. So we only need to focus on the even moments. Okay, so he actually denotes it by S sub R of P. So I'll also denote it by that. AP of EAB to the 2R. Okay, and he showed, so Birch showed that, so we are averaging over AB. So there's this P square many. So when we take an average, we divide by the total number as well. He showed that this is asymptotic to 2R factorial by R factorial times R plus 1 factorial times P to the R as P goes to infinity. Now it is noteworthy to see that these numbers are just the Catalan numbers. And those are known to be the moments of the semicircle distribution. Okay. These numbers keep popping up in a lot of areas in mathematics and no less in number theory, which are known to be the moments of the semicircle distribution.
Yeah.
Or is there a question or comment?
No.
Okay. Okay, so I'll just outline Birch's proof. Okay, so SR of P, which was 0 to P minus 1, AP of EAB to the 2R. If R is bigger than or equal to 1, we first take care of the bad pairs, the AB, so that P will divide the discriminant. So they account for P minus 1 plus, and the remaining, because we know that each of these will lie in minus 2 root P to 2 root P, we take this as T to the 2R, and then count for each T how many of these EAB would have contributed to the same T. So AB such that AP of EAB is T. And of course, these are the good pairs. Okay, so this comes from the bad pairs. And this whole thing comes from the good pairs. So the bad primes will contribute either 1, 0, or minus 1, and depending on the type of bad reduction. And so it turns out that, so here, because it's taken to an even power, it doesn't matter whether it's 1 or minus 1, but we only need to care about which one is 0. And it turns out there's only one case where it is 0. There are P pairs of bad primes, and one of them gives 0. Every others give 1 or minus 1. And so you get a P minus 1. Okay. Now, what about, so of course we need to focus on this one. Now, Deuting in 1941 showed that for each T satisfying T squared is less than 4P, the number of curves up to isomorphism with P plus 1 minus T points is given by this number H of T squared minus 4P. Here, H of N is the Hurwitz-Kronecker class number. Okay, and it is defined as the weighted cardinality of the set of equivalence classes of binary quadratic forms of discriminant n. Sorry, this should be positive definite. Okay, so the discriminant should be negative. And the weighted, what I mean by weighted cardinality is it's not like you just count each equivalence class with a weight 1, but we divide by the size of the automorphism. If two forms are isomorphic to each other, we have to divide by that because it would overcome. Okay, so here the equivalence class of a form F is counted with the weight 1 over automorphism of F. Okay, and here isomorphism of two forms is given by a matrix in SL2Z. So you can go from one form to the other. And if they're equivalent, then you see how many of them would take it to itself, and that would give the automorphism. But for most forms, it's just one. It's just in two cases where it'll be 1 over 2 and 1 over 4. But regardless, it's just a weighted cardinality. Okay, so if we plug this back in our earlier equation, so SR of P will be pi minus 1 plus t less than 2 root p, t to the 2r, h of t squared minus 4p. Okay, so this is up to isomorphism, but we're counting all of them, so we actually need times p minus 1. Okay, and now Birch did something interesting. He related this term to the trace formula of Heck operators on the space of holomorphic Gus forms. Okay, so Birch then related the second sum to the trace formula which is, so I'll explain the thing, but just showing you what the formula is. I'll explain what this is. So this is minus t less than 2 root p alpha t to the 2k minus 1 minus alpha t bar to the 2k minus 1. Okay, so you see this obviously sits, so of course there's some extra factor here where alpha t is t plus or minus square root of t square minus 4p by 2. These are roots of the appropriate quadratic equation. But you see that when you subtract with the conjugate and take powers, you will see powers of t coming in. So there is a way to go from here to getting t to the 2r. And sigma k of tp is the trace of the Heck operator Tp acting on the space of holomorphic Gus forms of weight k and level 1, the full level. Okay. And so he after moving this term to the other side, there's a p minus 1, we move it to the other side. So he gets 1 over p minus 1, SR of p minus 1 as 2r factorial, r factorial times r plus 1 factorial, p to the r plus 1 minus K going from 1 to R. So this is, I'm not going through the calculation here. P to the R minus K times sigma K plus 1 of TP plus 1. Okay, and then, so this is of course what we want. And it better be that this is smaller so that we can actually get an asymptotic formula. And he used the bound that sigma K plus 1 of TP is of the size P to the K plus 3/4 plus epsilon. So it's just smaller than 1, and that's all we need, because the largest term here is P to the R minus 1. And as long as this quantity, whatever the contribution of P is, it should be less than R plus 1. And so K gets cancelled over here, but then the remaining thing should be strictly smaller than 1. And so the other terms, of course, contribute smaller powers of P, so we can ignore them. And R is, it's the rth moment, so R can be treated as a constant. And so it doesn't matter how many terms there are, it just matters that each term contributes some, look at the contribution of the power of P. And so this gives 1 by P squared SR of P as 2R factorial P to the R by R factorial times R plus 1 factorial. Okay, so that is essentially his proof. And this, oh, of course, so this is as P tends to infinity. And of course, this doesn't prove the Sato-Tate conjecture, because we varied over elliptic curves and let P goes to infinity only after we finish the calculation. So that's why it's called a vertical variant. And so any questions about this so far? Okay, so then comes the question, what about error terms? Of course, one could try and write this in a more systematic way, but it seems rather messy considering we have this, and we sort of lose information when we take this bound. And so it is interesting to see if we can, oh, of course, this would be the error term in the moment expression, but we want to say, okay, we know that the main term should be the Sato-Tate measure. So let Ni of P be the number of pairs AB such that the discriminant is 0 and AP of EAB divided by 2 square root of P belongs to I. Okay. So Sato-Tate conjecture and so this tells me that this is, I mean, Birch's result. Okay. Tells me that this is asymptotic to mu st of I times P squared. Okay, but we want to know what the error term would be. Okay, so the fact that this is proved by the method of moments, we know that this is asymptotic to the Sato-Tate measure times the total number of pairs, which is P squared. We want to say, okay, can we get something like Ni of P minus, can we estimate this difference? Okay, and so this is something I worked on. So instead of studying the distribution of the sequence, we do a little change of variable where we let AP of EAB. We know it's bounded by 2 square root of P. So we can write it as 2 square root of P cosine theta AB. And so we look at the distribution of the thetas, so the angles. And so so what we'll do is we'll normalize by dividing by 2 pi, just because it'll ease. So we look at theta AB 2 pi in 0 half. And so what we want is AB belong to FP. So I'll put a star to denote that we're looking only at the good pairs. Pi of theta AB by 2 pi. Okay. And so the idea is that we can find trigonometric polynomials that can be used to majorize and minorize the characteristic function of an interval. So, right. So we have, okay, so there is these Berling-Selberg polynomials. So these are SM plus and SM minus, where SM plus will be an upper bound and this will be a lower bound of degree less than equal to capital M. So for each M, we have these polynomials, so it's a family, and they satisfy first the obvious one that we want them to be upper and lower bounds for the characteristic function of an interval. So of course, these will depend on I. So I should actually write this, but then I'll just suppress it because it will just make the notation more cluttered. And what we know, without going into the actual expression for this, what we'll only need is really the Fourier coefficients. So the zeroth Fourier coefficient will be the length of the interval plus or minus 1 over n plus 1, where the plus is for the majorant and minus is for the minorant. And for every other between 1 and m, we have that SM hat plus minus of m is of the size 1 over n. Okay. And these are all the properties we'll need to know. So what we do is, okay, for us, our x would be the theta AB, and then we would sum over little a, little b. So we have theta AB over pi. So I can have AB. So this is m less than equal to m. So I'll just do the upper bound. And so of course, so here you would have E of n theta AB by 2 pi. And so what we'll end up doing is we'll take plus or minus of these angles and then compensate later. And the advantage of doing that is that we would get expressions of the form cosine m theta AB. And these are the Chebyshev polynomials of the second kind. So we can actually translate this to be of the form AB belong to FP. So let's just isolate the zeroth Fourier coefficient. and to FP. The remaining terms. So we'll combine it so that SM hat of M and SM hat of minus M will add up, and I'll just write it as script M, script S. And I have UM of cosine theta AP. Okay. Now, so these are Chebyshev polynomials. Of the second kind. And it's natural to expect these things to pop up because this is a family of, so they form a orthonormal basis where the, with respect to the semicircle measure. So just like, and so we can expect these to show up when we are talking about the angles coming from AP of E, which we sort of already know that they're going to be equidistributed with respect to the Sato-Tate measure. Okay, but another bonus of taking this is that we can relate this to the trace formula as well. So going back to the trace formula, this thing actually, you can express it as this is UM of cosine theta t. Sorry, not M. This will be U2K of cosine theta t, where theta t is now, so for each t, we know that it's 2 root p. So we can write it as t as 2 root p cosine theta t. Okay, so this actually comes out as this. So it is natural to take this expression. So once we have back to this. Once we have this term, so let's just pull this out. So this is so script M. For M equal to 0, U0 is just 1. So that's why there's no other term coming along here. Plus M equal to 1 to M. Let's set M of M. AB belong to FP. UM of cosine theta AB. And then we do the same thing that Birch did, which is you relate this, instead of counting AB, we count it as you fix a t less than 2 root p, so that you have and you count the number of curves which correspond to the same t. Sorry, and so that will give me that times h of t square minus 4 times p minus 1. Okay. So now we use a trace formula to get a bound for this. Okay, so this use trace formula. So actually we don't even use this trace formula. So the trace formula is just the sum of the eigenvalues of the Heck operator. And we just use the Ramanujan-Peterson bound saying that each A of P, sorry, here it is of modular form. So AF of P is bounded by 2P to the K minus 1 over 2, where F belongs to SK of gamma naught of 1. So we literally bound all the eigenvalues by the maximum. So we're not really doing anything sharp there, but because we want the entire sum, we can't really do any better. Even if you use the trace formula, we'll get the same thing, but it's the constants work out better if we just take the simpler bound. So we do that. And for here, we use the fact that this is over 1 over M. And using the trace formula, we get this to be of the size mp to the 3/2. And so now we sum over m. We have a little m, this m gets cancelled. So you just have m p to the 3/2. So you have this thing. But this one, Sm hat of 0, if we express, once we express in terms of Chebyshev polynomials, this actually happens to be the Sato-Tate measure. So we get p squared times mu st of I plus 1 over m plus 1. And so we have the main term that we needed, p squared times the Sato-Tate measure. The remaining thing we'll have to, so we till now we've not, this works for any m, and we choose m in terms of p to optimize and get as small an error term as possible. So we get p squared times mu st of I, p squared by m plus 1. And we see that these two, for the choice of m being p to the quarter, would balance these error terms, and we get p to the 7/4. Okay, so we actually just saved just a little bit, and of course this is this will be a true error term only if the actual Sato-Tate measure of the interval is bigger than this. So otherwise it won't be, then this term will beat this term. But anyway, so all this is on one side, but we can do the same thing for Sm minus everywhere. So we get the main term as the same one, and these will also have a similar bound. And so we get ni of p minus p squared times mu st of I is O of p to the 7/4. So this was joint with Ramurthy. So yeah. Anyway, this is basically what I wanted to present. I'll be happy to take any questions. Okay, so I see there are some of my students here. I'm sorry if this was not at all accessible to you, but the idea is that there's a sequence, and number theorists are once usually the prime indexed ones will have a special behavior, and this. Okay, let me show maybe an actual picture of where is the. What do I have? Screen share or something. Okay, never mind. I'm having some internet thing. Anyway, so any questions?
I have this general question. Is this related somehow, means as the application with the modularity of elliptic curves?
No. See, yeah, this the fact that the trace formula is coming into the picture, it just shows some connection between the elliptic curves. But the thing is, the modularity will connect elliptic curves to modular forms of weight 2. And the level need not be, the level is the same as the conductor of the elliptic curve. But here the trace formula is relating the elliptic curve to the trace on SK, where K could be anything, and it's level 1. So it's kind of a different connection altogether. And it's really, it's just talking about the sum of these APEs, right?
So those APs actually appear in this kind of some versions of modularity.
Yeah. So modularity says that if
AP is equal to some BP.
if you take a non-CA,
correspond to Fourier coefficients of the modular form.
exactly. So what you get as AP of E here, and if you take the modular form, AFN Q to the N, and going from these coefficients will be the same if F is a new form of weight 2. So every elliptic curve comes from a new form of weight 2. That's what modular.
That is exactly modularity theorem.
Yeah, but see, but then yes, but then here, so this E will have some conductor N, and modular form will have some level N, and these will be the same.
Yeah.
But here, that's not happening. Here we are talking about the trace where the level is 1, no matter what your E is. E could have, different conductor, and K is varying. K is not fixed to be 2. You see, K is coming from 1 to R. Yeah.
So
it's just an interesting
conductor of the elliptic curve could be anything, right? In the Sato-Tate.
Yeah. It's for any elliptic curve. Yeah.
Understanding those APs would say something about no?
About what?
About the coefficient of the modular form to construct that modular form.
No, they're exactly the same. Modularity tells us it's exactly the same. That every elliptic curve comes from a new form of weight 2.
Okay.
So you can see this as a special case. The non-CM elliptic curves is a special case of a non-CM new form. That's what I mean. So you can imagine it's a big deal to prove that. So yeah.
Just to completely working over the Q case, Fresnel number field case. So far, no?
Well, I started with going over FP is like you start with an E over Q, and then you reduce mod P.
Yeah, but there are versions over the totally real number field also.
Yes. Yeah. So that'll go into Hilbert modular form.
And probably have some extra assumptions for the elliptic curve.
Oh, you mean elliptic curves over totally real fields?
Yeah. So Sato-Tate conjecture.
Oh, yeah. There are versions over for elliptic curves over other fields, also for Hilbert modular forms. I mean, Sato-Tate for modular forms is also known, like the AF of N. We know that this is 2 to the P is bounded by 2 to the P to the K minus 1 over 2.
Some Deline's proof, right? Deline's proof. Ramanujan conjecture.
Yeah. So Deline showed that this bound. So here how we have the Hasse bound, Deline's bound for the Ramanujan.
So showing this bound is also Sato-Tate something?
Yeah, you can formulate the same thing. So now you have this, and so now you can this is P. AF of P divided by 2P to the K minus 1 over 2 lies in minus 1, 1. And so you ask how this sits inside the sequence, and it's the same thing. So here, if I take it as Ni of F as prime less than X, for which AF of P belongs to I, by pi of X, this is asymptotic to the Sato-Tate measure. So this was proved more recently by Thomas Barnett Lamb, David Geracti, Michael Harris, and Richard Taylor. I think, yeah, this I think was 2011. But the elliptic curves thing was proved earlier, so that was like specifically, and then this of course implies the result for elliptic curves as well, precisely because of modularity. Yeah, in fact, in my PhD thesis, I studied the error terms coming from this particular version of Sato-Tate.
Modular form version.
The elliptic curve stuff I did afterwards. In my thesis, I just talked about this. Of course, I didn't see here. So there I did the error terms again on average. This is for a fixed f. So I took sum over and so that doesn't translate to sum over EAB. That's not, you know, that kind of relation doesn't work. So this was a different problem. Anyway. Any other questions?
No.
I forget where the histogram was. Anyway, maybe it doesn't matter.
No, I have no question. Go ahead.
Okay. Vaidi, would you like to end the talk?
It is you completed?
Yeah.
Actually, you ended last time some results from yours, right?
Yes.
Did you explain that? Not right.
Sorry?
I think you did not explain it. Did you?
Yeah, this is the proof.
Okay.
Yeah.
So does anybody have any other questions or comments about this talk?
Do you understand something about the elliptic curves over totally real field?
No, I only worked over finite fields.
No. So this Saturated conjecture over for elliptic curve over totally real field.
Yeah, I don't know what because see, I don't know what the bound itself on the coefficients are. Like I really have no idea. I just know that okay, you can formulate this, but I don't know whether it's even still a conjecture or it's, you know, because there's no, like I guess you can talk about primes in an extension. Okay, so here's another thing. So in terms of formulation, you can always formulate. I just don't know whether it is proved or not.
I think it is true, but yeah, so there would be some trickiness or some difficulty to formulate itself a little bit. Not very difficulty.
No. So the thing, formulation is not the question because so Sato, this is like Sato-Tate, right? So Sato, he conjectured using numerical data. Meanwhile, Tate actually got it more like a conceptual thing. So if you have a compact group G and you take the set of the space of conjugacy classes of G, you can define the equidistribution of a sequence in X with respect to the measure, which is the push forward of the Haar measure on G. Okay, and that the theorem is that this equidistribution will happen if and only if a certain L function has analytic continuation, which is non-vanishing and holomorphic in the complex plane, except at real part of, at S equal to 1, except for a pole. And for the case of G as SU2, the push forward the Haar measure is exactly the Sato-Tate measure. And Tate conjecture that required L function has those analyticity properties. And that's how Tate conjectured that you should have this distribution for modular forms and elliptic curves. So there the prime, so you can take your G to be, take it as a different group, take your, oh yeah, and the L function is corresponding to the irreducible representations of G. And it comes to be something like, okay, maybe write it down. So it's something like L rho of S. So here is the irreducible representation of G. And so you fix a number field K. And you take a sequence X rho, where XP, where P are primes in K. Okay, so just like how the AP of E are indexed by the rational primes, you can take a sequence indexed by primes in a number field, and so you have so if you just take set of all primes, this is what norm of P inverse. So this this L function is what is like you need the analyticity. I mean, you want this to extend analytically to the whole complex. So this is valid for real part of S bigger than 1.
My point was just that if you are comfortable with the working over the totally real field,
No, I told you I have just worked over finite field, but I know that you can formulate it for any totally real field. So Tate's conjecture is sort of true in more generality, but
this particular trimester is more focused about the open things on the. So over the Q, most of the things are known, like modularity conjectures are known and other things. So over the totally real field or even quadratic real field, things are open. So and we will have proceedings also perhaps.
Okay.
So you can consider, and there will be some time, good time frame to prepare some article or something.
Yeah, I'm sorry, Devendra. I'm really like swamped with so many things. You know, I
was just
back, it would have been fine.
Yeah.
I got your email about the proceedings.
No, so that was the previous thing and previous trimester, and this is for the new trimester.
Okay.
It will be different editorial board and different kind of probably policy.
Okay.
Policy is not decided. We are finalizing the editorial board.
Okay.
And so it would be more number theoretic. Whatever I asked you for the previous trimester, it is working. So that was more geometric.
Sure.
More arithmetic. So my was just question so it would be more fitting. So point is that the contribution should fit coherently with the overall theme, right?
Yeah, which is why I'm saying that I don't think I'll be able to contribute.
But I don't know, means maybe people can want to go random, the kind of proceedings generally happen. So it will depend.
Okay.
So in the first trimester, we decided that we should have a coherent thing and we should have something pedagogical because there was not much new research talks. But this time there are more recent research we are discussing. So we want to present it in some novel way.
I see. Okay. That's a very nice venture.
Okay, so
we end the meeting?
Yes. So does anybody have any comments? Because I can see a few of my classmates. If not, then we would like to thank Neha Prabhu for this very wonderful talk.
Thanks, Neha.
Thank you. Yeah.
Thank you.
Again.
Yeah.
Bye.
Okay, see you. Bye.